is skilled technically in ligandography, molecular dynamic simulation, thermodynamic integration, homology modeling, and many more. He published more than 10 key research findings in national and international peer-reviewed journals. He also presented his talks on various national and international platforms. With this brief introduction, I heartily welcome you, sir, and thank you for accepting our invitation. Now I request Dr. P.M. Ronan to welcome their speaker. Thank you, sir. Now we can take it.
We'll go back. Just for YouTube purpose, you can hang it here. That's the best. And this is
The letter is also coming.
so you don't need that.
Okay. So yeah, good afternoon, everyone. Myself Subhamay, and first of all, I'd like to thank the organizing committee and the entire KLE College of Pharmacy fraternity for inviting me to attend this special session of this faculty development program. Now, I am currently working as an assistant professor in the Department of Chemical Engineering at IIT Dharwad, and my research mostly lies in the interface of computational chemistry and biology, and as part of which I apply several computational chemistry tools and techniques such as molecular docking, molecular simulation, free energy calculation to understand the physics and functions of proteins and other biomolecular structures. For example, how enzymes catalyze its reaction, how drug molecules bind to its target protein of interest, or what excipient or solvent you should select to enhance drug solubility. And this kind of studies have immense application in the domain of pharmaceutical industry. Now today I am going to talk about one of such computational chemistry tool which I routinely use for my research, and that is called the molecular docking. And this is the title of my today's talk. Now here I would like to highlight that this today's talk will be helpful for them who have never used molecular docking, okay, as part of their teaching or research purpose, but definitely they want to try it out in the coming days. And this talk will be also helpful for them who have used molecular docking, but used as a black box without realizing the fact what are the theories and principles behind it. So I do believe that my talk will be helpful for both of them. Okay. So without further delay, uh, let's look into the content of my presentation. So I have divided my presentation into four components. In the first part, I'm going to talk about the overview of molecular docking. Means that what exactly is molecular docking and why do we even bother to use it? And if it is so, then what are the kind of applications we are expecting from molecular docking, right? And I will also show you some case studies to prove my point. Then definitely I'll be in the second part I'll be talking about the physics behind molecular docking. Okay, what is the underlying theories and principles behind it? And then the third component I'll be also talking about the recent trends, what exactly going on in the AI ML field, and how they are contributing to this molecular docking aspect. And finally, I'll be also briefly talk about beyond molecular docking, what else we can do and why we should do that. Okay, so these are the four components I'm going to cover. And let's move with our first topic, that is the overview of molecular docking and its applications. Okay. So what is molecular docking? Okay. The molecular docking is the in silico study of how two molecules fit together and facilitate favorable interaction. So when I say in silico, it means we are not going to go to the wet lab. Rather, we are going to do this study in computer. As simple as that. Now, what exactly we can do? It basically allows us to understand how two molecules selectively recognize and interact among themselves and facilitate many physicochemical and biological functions. Okay? So now some of the examples which I can give is the how drugs are interacting with the protein. Even we can think about how antibodies recognizing antigen. Even we can think about how receptor molecules are recognizing the signal molecules, or vice versa. But these are purely applications which you are seeing in the biological aspect. But think about that docking. What is the definition of it? It really doesn't talk about whether it is protein or ligand, right? It is basically two molecules and coming together and whether they are interacting or not. And these two molecules can be anything. So essentially, it means that it's not only in the application in the biology. There are certain other areas also you can apply the principle of docking. For example, if you are really interested into development of the biosensor, so you basically want to study how protein is interacting with the gold particles, gold nanoparticles, right? Even like if you really want to develop a metal organic framework, so basically you can think it as a material which selectively recognizes pollutants like dry molecules. So basically, based on that, you can design a metal organic framework which will help you to remove the dyes or the other pollutants from the water. So these are the other areas beyond biology also where molecular docking can be used. Okay. Now the second question is that when should we think of doing molecular docking? It's not that okay, I want to do molecular docking and that's why I will do it. It's not like that. There has to be some rationale behind it, right? Okay. So if there is no way to know that whether two molecules are going to interact or not, you have no idea. That time you should use molecular docking. Okay, I'll tell you why. And then somehow, other way, you know that these two molecules interact, but you do not have any other information like what are the atoms involved, what is the nature of the interaction is behind it. You do not have any clue. That time you should do molecular docking. Okay, so just to give you an example, so you have here two molecules. I'm not going to say protein or ligand, two molecules. Okay, and one of them is is receptor, which we are familiar with, and another is a ligand. Now, I have no idea whether they are going to interact or not. This is the time you may try out molecular docking. And now, for somehow through some biochemical studies or some inhibition study you have done, and probably you know either the IC50 value or the KD value. That information is with you, but you do not know where it is binding or what are the atoms involved in there. That time only you should do the molecular docking. And this is the typical process which you do. As I said, that molecular docking is the computational study. So you are going to do the study in the computer, and then further that you do the analysis. So you are going to come to know that what atoms or what components of those particular molecules are interacting with among themselves. And then what is the nature of interaction? Is it a hydrophobic interaction, polar interaction, okay, hydrogen bonding, salt bridges? What kind of interaction it is happening? That nature of the interaction also you can assess. And finally, you will also get a rough estimate like of a binding affinity or binding score or docking score, we often call some energy score, which basically tells you that how good that compatibility between those two molecules are. Okay? Now, why should you bother to learn all these things? Again, if I'm interested, then only I should do the molecular docking. If I'm not interested, why should I do that? Right? Okay. This is the most important thing. If you know these three informations, okay, then what we can do? We can do the molecular engineering, basically, which will help you to either improve or reduce the strength of interaction. Okay, as per your need. For example, if you are thinking of drug discovery and you know, say, the mechanism of action and you know the natural substrate and you want to develop a substrate analog of it, and probably you want to improve the affinity with the target, that time probably if you know how the natural substrate or natural ligand is interacting with the target protein, essentially you can do further modifications in the molecule and try to improve the interaction. Okay, so this information is what you require for doing any kind of engineering. And as I said before, when you have no idea, that time you should the molecular docking. And whenever you have some experimental data like IC50 value or KD values, still you should do molecular docking because you do not have any of these structural informations, right? That's the reason you should do the molecular docking. Fair enough? Now, how this molecular docking is impacting pharma industry? So I have said a lot of things, but I have to make my case. Otherwise, why should you believe me, right? So this is probably a well-known graph well-known plot to you. This basically shows you what is the timeline and what are the steps involved when you are actually developing a therapeutic drug. Okay, and if you look at, I'm not very sure that whether it's visible or not, but at least you can see that there are 5 steps. Okay, and out of those 5 steps, the first step, it takes basically 4 to 7 years. It's basically the step where basically doing some fundamental research as well as doing preclinical study. Following which you have third and fourth stage. It's basically your clinical studies are going on, and then finally in the fourth stage, your FDA is going to review your data. And here you said that this third stage it takes around 8 years, and the fourth stage it takes 2 years, and then when you launch the drug product in the market, and then you do the continuous monitoring of that. So these steps 3, 4, and 5, this is pretty rigid. You really cannot reduce the timeline or anything, okay? Because this is not in your hand. Okay, what you can actually do in terms of research is that you can really play with this area, particularly that first step, the initial discovery and development. If you are really, really smart, or you are using tools which can accelerate this process, it will significantly reduce the timeline, right? But that is also not the purpose of using molecular docking, just to reduce the timeline. Okay? It is another aspect of it. To make your molecule to work in the later stage, okay, you have to do very good research in the initial stage. Okay, if you don't do good research, even if you after 7 years, when you go to the clinical studies, you will come to know that okay, your molecule is failing. It's a complete wastage of your time, resources, and whatever you are using. So that's why a very good research work has to be done here. Okay, and for that we have to understand for what are the activities, major activities going on in this step. Okay, so first stage is pretty straightforward. So basically you are going to define or identify what is the target, okay, or what is the target or protein or whatever you want to say it. So what is causing the particular disease? You can do some biochemical studies, you can do some knockout studies, okay, mice knockout studies and all. But figure at the ultimate point is that you are basically identifying that particular target on which you should work on. Okay, and then you do some further characterization. Probably you want to do some extra studies or NMR studies to resolve the target structure. Okay? Once you have characterized your target, or you have known your target, then the second thing is that now you have to either augment its function or you have to inhibit its function, right? And that way, that only you can do uh, with some molecules. Okay, and there are a lot of databases available like PubChem, Campbell, Jink, and so on. You can use those databases, and then basically want to see that in those databases, whatever molecules are there, okay, out of those molecules, which are actually going to do complementary interaction with this target. And this is I have put like 3 figures to explain the same thing, but trust me, this is the most time consuming process if you think of experimentally. Just to tell you that, so you basically synthesizing every molecule and then going to the lab, okay, and when you are synthesizing the molecule, there itself has a problem. You first of all, many of those are chiral molecules, and you don't know the chirality of the molecule itself. Okay, you are sending your sample multiple times, they are doing NMR and all, it's a mess. Okay, so and then if you have to do this kind of activity for thousands, millions, billions, trillions. After that, I don't know how to count. But I will tell you that there are 10 to the power 64. Avogadro number is 10 to the power 23. 10 to the power 64. And even more chemical space is there. And that is also not captured in this commonly available databases. So 10 to the power 64 means after one, you basically put 64 zeros. Those many chemicals you have to synthesize, then you have to have an assay for it, and then you have to assess that the binding affinity or inhibition constant, right? It is basically impossible. So that's why we are going to do this docking over here to reduce that burden, right? And once this kind of a funnel, okay, so you have a lot of possibilities and you are using a tool to funnel it further, so that now instead of the 10 to the power 64, forget about it, the number, at least if we can come down to say 100 or 1000 molecules, then still we can manage or handle, isn't it? So that's the major purpose of docking. And then once you get to know your molecule, then following with, you can start doing synthesizing and do the further preclinical studies. Now then what is the role of the docking? Docking actually significantly reduces the time. It basically helps you to quickly identify the lead, and if it is required, it is going to help you to optimize the lead further, and it significantly reduces time. But that is also not the purpose of docking, as I said. It basically allows you to screen number of molecules which human can never imagine. Okay, so for example, I am say Mark, and my colleague is from GSK. Probably we are battling for designing or developing a therapeutic drug which is basically aiming to block the same target. You have to think about it. So if we are following the same path, okay, and if he is before me, he will find the solution before me, right? And if we are playing with a limited number of space, okay, so I have 10,000 molecules. He has started this program. You will find the right solution before me. So then I am losing the business, right? So that means I cannot take just 10,000 molecules. I have to try out some other pools, isn't it? And that's the reason. That's the reason that docking is a tool which actually allows you to explore the molecules which you can never imagine. And the third thing also I tell that it's basically going to reduce the risk factor for failing the molecule in the later stage. Okay. Is it clear as of now? Because see, when I teach, first of all make sure that someone, when I teach, instead of talking about a lot of theories, people should understand first why we should do that. If there we do not find motivation, then we should not continue further. Okay. If we are motivated, then only we'll do. Okay. So now this was my one earlier slide was only about the drug discovery. What else you can think about? So if you're really smart, so for example, you have a drug molecule, you know it works, okay, but you don't know for which target. It's basically now the backward calculation. Now you can basically identify the target. It's called a target fishing. So you know the solution, you know the problem. You don't know the problem. Okay, so you use the same analogy to define the problem. Okay, it's like that. This is called the target fishing. And we talked about this virtual screening. Virtual screening is basically docking in large scale, I would say, but the purpose is same. Okay, identifying the molecules. And then ligand target binding rationalization. If anybody are from academia here, okay, in different colleges, you know that whenever you are doing some studies, okay, if you submit your article in some journal, they will ask for, okay, what is the reason? Please put some rationale and why this particular ligand is working on this particular target. Rationale means those molecular details which I showed you, that what atom is interacting with what, and is it consistent across the same family or same class of molecules or not. That rationale you have to get. Okay, and this kind of ligand target binding rationalization also you can use the molecular docking. And essentially, and these are the basically off target if you want to explore. For that also you can use the molecular docking. And polypharmacology and drug repurposing or repositioning, for this kind of applications also you can use molecular docking. Okay, I told it, but is it that everybody understood it and using it? Okay. But for that I have a statistics. I wanted to make sure that whatever I am saying, everybody is understanding it across the world, and they are already in the process of utilizing it. And this statistics actually tells you the number of publications where that word keyword docking has been used. Okay, so basically it generally tells you that the number of publications where docking they have used. Okay? And you see that in 2000, the number of publications were very less where the docking software is used. But over the course of the time, this is the last update I have, 2020. So you can see the 9,000 or 10,000 publications they have mentioned this word called docking. So it essentially means that slowly this particular approach of technology is being accepted in the community. Okay. Now, okay, I understood the more importance of molecular docking, but what exactly, I am saying that, okay, it is very routinely being used in many development process, but now I'm going to show you a case study where literally docking was used to discover a drug. I would not say discover, design a drug, I would say, design an inhibitor. So this is this drug called zanamivir. Okay? So this is the first-in-class drug to treat influenza virus. So this is a human neuraminidase inhibitor protein. Okay. Now, if you look at the 2D structure of this zanamivir drug, you will see that you have this group, and at this end, particularly look at this 3 nitrogen. This is called the guanidine group, and this is the major group which actually inhibits, actually increases the binding affinity of this particular drug to this neuraminidase target protein. Now, what we are going to show you that how these guanidine groups, these 3 nitrogen groups, have come into the picture. Okay? So now this particular, and this is the first time the case where molecular docking software called GRID was used. I'm talking about back in 1985. Okay, 1985. This particular time, first time this docking concept has come. Okay, the principle was long back, but in reality, one software being used to do the docking. This was the first case. So if you think about this neuraminidase protein or enzyme, okay, so this protein's natural substrate is sialic acid. So this is the sialic acid shown in green. So what is the similarity and differences? Only difference is that instead of these 3 nitrogen groups or guanidine, you have hydroxyl group over here, OH group. Okay? And what is there here? It is here. Okay? This is the OH group. Here, whatever I am showing in the figure, the red ones are actually the oxygen atom. Okay? Now, this complex also was not known to us. This how this natural substrate sialic acid interacts with this. What is that called? This neuraminidase protein enzyme. Okay. And what we did, what they did, they basically used this docking program and they docked this sialic acid to this particular protein. And what they found that there are several polar residues like arginine 371, glutamic acid 119, and then glutamic acid 227. Okay, and they found that particularly this arginine 371, okay, that is making salt bridge interaction with this acid group. Acid group is nothing but this particular group. Okay? Whatever I am showing here. Okay, this is making salt, so that is good. But the issue is that this hydroxyl group, though there is this glutamic acid 119, it was not making very good interaction. So what they did, they instead of this hydroxyl group, they changed it with the amine group. Okay? And then they are able to observe some hydrogen bond interaction with this glutamic acid. And then they also found that if this molecule can be further extended, then there is possibility that they can interact with one other amino acid called glutamic acid 227. These are all, charged residues, negatively charged residues. Okay. So in that line, what they did, so they added additional these 2 nitrogen groups. Okay. So now you can see that interaction is basically complete. And towards from the left hand side to the right hand side, it's basically you can see that the binding affinity, the inhibition has been increased, and this is your final drug. So I will not say this is drug discovery, but I will say that it's basically modifying a natural substrate to its analog, which finally led to this particular drug. Okay, and these entire studies were done using molecular docking. People had no idea, okay, what is going on here. So they used the docking software to understand the 3D interactions, which I talked earlier. And based on that, they redesigned the molecule. As I said, that molecular engineering they have done, and they increased the affinity. Okay. So next, I will go to another case study. Okay? So it's a little bit beyond drug discovery. So here, I will talk about how this molecular docking was used in biocatalysis. So this is a drug, sitagliptin. Okay, this is used to treat type 2 diabetes. So these are the formal details. Now, the typical route of synthesis of this particular drug is that this is called the chemocatalytic route. So you have a pro-sitagliptin substrate, which you have the keto group, 2 keto group. Then first what you do, you use ammonium acetate, and one of the keto group is basically reduced to enamine. And then further, you use some metal catalyst. Here, I'm not very sure whether it is visible or not, but this rhodium. And then when it interacts with it, this particularly is going to give you the sitagliptin product. And now you look into here, the purity of the product which you are getting. This is the drug sitagliptin we are talking about. This is 97% enantiomeric excess you are getting. Not only that, you are using metal catalyst, and this particular reaction is happening at 200 bar pressure. 200 pressure means like we are sitting in the 1 atmospheric pressure, 1 bar pressure. 200 times of that. So means that if I have to manufacture this API in the chemical plant, what I have to invest a lot of energy to generate that kind of huge pressure, 200 bar pressure, right? This is basically a huge investment. Not only that, you are using metal catalyst over here, and essentially this basically is even mixed with your drug. That's this product, okay, and it's very difficult to separate. So that's why this chemical initially though it was started, but now it is not being followed. And what is the route now? There is another route is called the biocatalytic approach. So what happens here? Instead of this metal catalyst rhodium, they used a transaminase enzyme to do that same reaction. Okay, transaminase reaction. And what is the advantage? Definitely you are using mild reaction conditions, and the purity of the product is now the 99.9% enantiomeric excess you are getting. Okay, and mild reaction conditions you are using. So that's it. So, but the question is that why we are using molecular docking here, right? Good, good. We are talking about biocatalysis, right? So I'll tell you this. This particular enzyme which is being used, transaminase, it is not the naturally occurring enzyme. Okay, they have used an engineered enzyme. Okay, so then essentially question is that okay, why they require engineering of this particular enzyme, right? Now to tell you this, so whenever they did some initial biochemical studies, this is the pro-sitagliptin substrate, this is the precursor. So when they studied it, they found that this substrate, the enzyme is not showing any activity to this pro-sitagliptin substrate. Okay? But this transaminase is actually showing a lot of activity towards the similar kind of substrate, acetophenone. Okay, the wild type enzyme I'm talking about, because we are talking about that we are using engineered enzyme to manufacture the sitagliptin, and then now we are explaining that why we had to go for enzyme engineering, because simple that wild type enzyme is not showing any activity towards the pro-sitagliptin substrate. Okay, and then what they are basically doing, they are basically doing to understand why it has shown. And what they did molecular docking. And if you can see that this is a very bulky substrate, so it really doesn't fit into the active site of the enzyme. And this is what we are talking about docking study. Okay, so they understood it, right? And then they somehow wanted to make sure that the space in the active site has to be broadened up. So they did some side chain mutations, okay, so that this particular bigger substrate can fit into the pocket now, and that is exactly what they have done, and ensuring that the key molecular level interactions are maintained. So in this way, they went to the details, they went to the active site of the enzyme, they did molecular docking studies, and finally they figured out that what is the problem or bottleneck, and they try to resolve it, and that is exactly lead to this engineered enzyme. This is the way you can also use or take leverage of molecular docking. Okay, this is a little bit different. So docking in drug formulation. Okay. So molecular docking, as I said before, it is basically the study, computer-aided study of how the two molecules are interacting. It really doesn't restrict you to study or into only receptor and ligand. Okay, it can be anything. So with that vision, so molecular docking can also be used to assess the stability of the drug formulation. So this was what done when I was in Becton Dickinson. So I collaborated with Sun Pharma, and that time we basically wanted to create a formulation for alectinib. So alectinib is an anti-cancer drug. Basically for lung cancer it is being used. So we wanted to improve the stability of the formulation, and what we wanted to do the change is that in the existing formulation we added one polymer called soluplus. Okay, so and now if you look into the extreme right, and we wanted to explain that how this alectinib is interacting with the soluplus, and if you look at the extreme right, this beads you are seeing, okay, this is basically your alectinib drug. This is the basically same thing which you are seeing here, and it is as adjacent to it you are going to see the some part of the soluplus, and we wanted to understand what is this interaction. Okay, what is the governing factor of having this formulation very stable, and we found that there are very stable interactions, hydrophobic interactions in nature, which are basically stabilizing it, this interaction, not the polar interactions. Okay, so this kind of molecular level details also you can exploit, and what you can do is that you can further redesign the polymer also if needed to even control the drug release or formulation stability, whatever you want to say. Okay, so as I said, there are a lot of different areas which you can apply molecular docking. Okay, so at least we are done with the first part. I think I don't know like whether you are motivated or not, but I find this tool is very fascinating, particularly for them who are willing to do the molecular engineering or in the near future. Now it is for them who have used molecular docking but without understanding what is the philosophy behind it. Okay, so now, and honestly speaking, I will try my best to make it non technical, but some places, please excuse me. Okay, so again, I'll come to the first, even before going to the docking part, we have to understand the philosophy that why, what should be, if I have to develop a software today or some program today, what has to be there, what principle has to be there, right? There the question comes. So for example, you have a receptor and ligand, okay? And then you have a tool, like say X-ray, crystallography, or NMR, any kind of structure, and you found a solution. Okay, yeah, this receptor and ligand is forming the complex, and this is how it should look like, okay? And this is the path. And path is basically clear, your experimental studies, X-ray or NMR structures. Now, you have to understand how, if the receptor was there in the solution, ligand was there in the solution, and in reality in the they are making the complex, how it is happening. So there are a lot of models to explain that. Why we have to learn the model, I will tell you later on. So basically, you know the starting point, receptor and ligand. You have the end point, and this is basically the path. And path is basically what it is explaining that how this receptor and ligand complexation is happening. Okay, and this is called the lock and key model, induced fit model. There are 2-3 models are there. Okay, I'll just tell you because this is very, very critical. So lock and key is basically very simple. Okay, so that you have lock and you have key. Lock can be anything, the key can be anything. The only thing that for our discussion sake, lock is a little bit bigger. Okay, and then we assume that this is target, protein, enzyme, whatever you want to call it. And key is basically drug, inhibitor, ligand, substrate, whatever you want to call it. But the main philosophy here is that only the correctly fit sized key fits into the keyhole. Okay, Tera mera keys are not going to work. Okay, only the correctly sized keys. Okay, a smaller key is not going to work. Larger key is not going to work. Otherwise, your house are already being robbed. Okay, so that is the principle. And if you look it over here, you'll see that this is the protein or whatever you want to call it, and this is the ligand. Okay, and look at the shape of the interface. It's practically not changing at all. Okay? I actually wanted to give you the example. I brought this pen also. So this is the your lock. If you think of the head of the pen, this is the nib. Nothing. I mean, it will fit only to this. Okay? This is the lock and key. But one thing is very important to understand that nothing is changing. It's basically if this is my lock is fixed and this is my key, I can move this key to over here. Okay, but this key I am not bending or distorting anything I am doing. It can move from here and there. It can come from here and there like this. Whatever it can happen, but I'm not bending it to fit it into the lock. Okay? Please keep that in mind. This is one way of explaining that how that complex has been formed. So you have the receptor, you have the ligand, and without any distortion or anything, it just ligand simply comes. This is ligand, you assume ligand simply comes and fit into the receptor. That's it. Now, this is lock and key. Second thing is that life is not always easy. So, so what happens is that definitely other model came because lock and key model was not able to explain all the cases. Okay, so what happened? This is the case where when you have the target, you have the ligand, and they are coming close to each other, and you will see that when the complex is being formed, the interface shape has changed. Okay, so basically what happens? This is called the induced fit model. So first I see that okay, I want to bind there, I'm going there, and once I come closer to it, I am basically forcing the near vicinity of my interaction to adjust so that I can do better interaction. This is called the induced fit. But here the conformational change of the protein or ligand, what you can say, it's like a optimal. It's not that significant change. And then there are cases, and that is what we call the induced fit model. Okay? And then there is another thing is called the ensemble model. Ensemble model, what is that? That the proteins are very, very flexible. They can attain any conformation. And what happens that maybe one particular molecule is blocking or interacting with one particular conformation of the protein. One molecule is basically meant for one particular conformation of the protein. Okay, so whenever I'm saying this is typical case for GPCRs. Okay, if you know about it, so you have agonist, you have antagonist. Okay, and it's basically bind to the same orthosteric site, but the molecules are different, and that's why the downstream effect is also completely different. Okay? It's like similar kind of approach. But again, I'm talking about it that rigid docking, there is no conformational change of the ligand. When I'm talking about induced fit docking, that time there is very optimal conformational change. And when I'm talking about the ensemble docking, that time particularly targets conformational change is huge. Okay. Now again coming to the docking. So because I want to develop a software, right? So I have to add some principles there. Think about it. So this is my starting point. This is my end point, right? Say I have obtained from X-ray of crystal structure, and how that complexation is happened, I use these three models to describe. Now think about the situation. You have the starting point, you don't know the end point. That's the problem, right? We are talking about. You have starting point, you don't know the end point, but you have some principles. So now if you want to develop a software or anything, computer, at least you have to ensure that these principles or models somehow or other way, partially or fully, has to be in that program or software, right? Because now this is the path. You have the starting point, end point. At starting point, you don't know the end point. At least path, you try your best to define, right? So that hoping that okay, you will into the desired end point, right? So that means if that is what our molecular docking is, then these principles to a certain extent has to be incorporated into our software. And this is the origin of molecular docking. Fair enough? Okay. So now since we talked about those three models, so one thing we came to realization is that rigidity, flexibility, conformation, all those terminology we have seen. And then we have to understand what is it. Okay. So this is why comes the physics part. So rigid body motion and molecular conformation. Okay. So for example, if there is a molecule, say this is a carbon dioxide molecule. So it's basically moving, going back and forth. Basically, it's called the rigid body motion in the form of translation. Okay. Then there is another kind of motion, it's basically rotation. Okay. So you are basically rotating all the 360 degrees wherever you like. Right. Another, but these two, I wanted to highlight that this translation and rotation are rigid body motions. Rigid body motions is like that basically I am the person, I am rotating like this, I am going like this. Okay. But it's not talking about that, okay, I am, flexing my muscles and, bending my legs and all. This is not telling it. This is what it is about the torsion. Torsion is basically how I am doing it, the things, okay? How I am stretching my head and legs. Okay? This is called the torsion. But this is called the rotation, translation or rotation, okay? So this is basically happens to the case when you have basically find rotatable bonds and you basically try to play with the torsional space, basically dihedral angle you want to change with. That time this kind of movements are going to happen. And this is basically generating a lot of different conformations. Now, when we talk about molecular docking, it basically is the amalgamation of all these three movements. Okay. And that is exactly what we are going to see here. So you are going to see the translation, rotation. Now you cannot distinguish, okay, clearly. But at least you can see that some this like distorting, dancing and all, but some translation, rotation are also happening at the same time. Torsion is also happening. Okay. And now only you hope that you will find the best pose. Fair enough? Now with that philosophy, so we wanted to talk about lock and key model. We talked about the conformational change. Now we understood that, okay, what exactly we mean by conformation. For that we have to understand the rigid body motion. Here there are no conformational changes involved. Only the rigid body motion is happening. And then if we play with the torsional space or dihedral space, where basically I am stretching my hands and legs or flexing my muscles, that is the torsion we are talking about. And amalgamation of all these three movements are going to give you the docking which you are looking for. Okay. Now, with that principle in mind, when we are trying to develop the docking software, there are different type of approaches, like something called rigid docking. Okay. Rigid docking is means that receptor is rigid. Okay. Rigid because it is bulky. There is no point to make it move, right? So always like if why you go to the temple or church, okay, God will not come to you. You have to go there. Because you are lighter, right? So basically you are ligand. So for ligand, when I'm talking about rigid docking, I'm talking about for ligand rigid body motion. Means it will be only happening translation and rotation. So if you think about the lock and key model, it's like if it is like the, say this molecule is like this, okay, I want to fit it. It is rotated, translated, and now it fitted. Understood? So this is called the rigid body motion. Okay, here I am not bending my pen. Okay, with the moment I start to bend my pen and all those things will happen. I mean, in parts, it will basically we are playing with the torsional space. Okay? So this is called the rigid body. This is called the rigid docking. Okay. Now you can closely correlate with the lock and key model. Then it's called the semi-flexible. The semi part is very difficult. It is like half or 25%, 70%. Very semi is I never understood it. But again, receptor is rigid. Nothing is changing. But ligand, translation, rotation, and also it is playing with the torsion. Torsional space. Three things are happening at the same time. And this is the most commonly used technique, semi-flexible docking, whenever you are trying to do dock. Okay. So your rigid receptor is fixed and you want to do the ligand to explore all the conformations in all the possible directions. Rigid body translation, rigid body rotation, and in torsional space also you are going to change the conformation. And there is something called flexible docking. This is again confusing. Okay, flexible docking means that ligand I have addressed everything. There is nothing left. Translation, rotation, torsion I have done. Only thing you are left with is the receptor. Okay, so receptor also I made it very confusing. Partially flexible. What does it mean? Okay, so we talked about these three motions of the ligand, but now think about the receptor. Okay, this receptor also is moving. Okay? So now this is becoming a very challenging problem. I will tell you why. But when I said the partially flexible, here you see that as the entire protein is moving, but instead of that, I'm only talking about that only a particular region, probably the active site of the protein, maybe some specific residues. I want to make it flexible. That is the time only I am saying that this is called the flexible docking. Okay, so protein is flexible in the torsional space, but only certain amino acids in the active site. Fair enough? So now when we talk about this complexity, because see, the moment I talk about computer, the first problem is that, okay, what is the RAM size I require, what is the memory and all those things I require. So this is the problem. Okay, that first of all I have to make sure that what laptop I want to buy. Okay, so 30,000 laptop is there, also 90,000 laptop is there. And if you want to do, so it is like a trick I used to use in my school days. Okay, I used to watch movies, but I used to give the name of my school projects, and okay, and I basically looted my dad. This is the same logic, but at least you should have a proper justification that, okay, how much computational power you require, and for that you have to understand this rigid docking. I am only talking about rotation, translation and rotational motion. Basically, rigid motion I am talking about. So essentially, it will be computationally less intensive. Okay, so with normal 30,000 computer or 20,000 computer, you can deal with it. Okay, result you will get whatever look that I do not know, but at least computer wise at least you will reduce the budget. Okay, but this one when we're talking about flexible docking, okay, it becomes computationally very intensive. Okay, and whenever the protein entire motion you are considering, okay, it will be your computer will definitely crash. I'm pretty sure about it. But the point is that more and more computational time you will require, more and more flexibility will consider. So now think about it. So you have, say, this is the three things. Okay, I mean 4 points you require to define a dihedral space, but 4 points. But I want to say that if you have bigger molecule, very big molecule, you will be having more degrees of freedom in the torsional space, right? So then for bigger molecule to dock, it requires even more computing power. Understand? And honestly speaking, when you are doing drug discovery, you really don't want to restrict it yourself, right? Because at the very beginning, if you use Lipinski's rule, then there will be nothing to optimize later on. So at least at the initial stage, you should not you do some fair, filtering, but do not do too strict filtering. Then you will not get anything out of it. Okay. Okay, still we are talking about physics, and we didn't start even the physics. We basically are still talking about the principles of molecular docking. What are the things to be there in the molecular docking software, and what type of docking algorithms are already available, right? Now let's look into our straightforward thing, this conventional protein ligand docking. So we talked about conformations. We understood the complexity of the conformations. More time is required, more computing power is required, that we understood. Now, if you look at the typical protein ligand docking, there are two steps. One is the post generation. So you have to sample everything, all the possible conformation, and you have to find the best pose, right? Which gives the most favorable interaction. So when I said two things, best pose, so pose has to be generated. So basically your ligand has to roam around and finally find the exact pocket and then find the exact orientation it loves to interact. And then how do I know that this is the one? Because as I said before, you know starting point, you don't know the end point, okay? And then there has to be a mean to at least define that, okay, this is the, I would not say best end point, but actually whatever results I got on with respect to that, it is the best solution. Okay? So we have two things to do. One is called the post generation, another thing is called the scoring. Okay, scoring. Two factors are there in the docking. So now let's look into the post generation. Post generation is basically what? Amalgamation of all the three kind of movements. I mean, rigid body motion, translation, rigid body motion, means translation and rotation, and the torsional freedom. Now, what is the objective? To identify or reproduce the experimental binding pose as early as possible. Right? That is what you want to do. Now, this search algorithms, again, this is a lot of theoretical stuff. I'll explain to you in layman's way. So there are two algorithms are available. One is called systematic search, and another is called the stochastic or random search. Too much. Too much. I'll just give you an example. Okay. So, okay, what do I like to have? Coffee or tea? How do I know? Very easy to know. It's basically you put a CCTV in my house, and entire day what I am drinking, what I am doing, record it. Okay. And then at the end, at night, you see the entire recording, and you will find that in the morning I'm drinking hot water, and then maybe most of the time I'm drinking tea. Sometimes I'm maybe one or two times you're seeing me drink coffee as well. And based on that, you will be doing your analysis and you will find out that probably I do like tea over anything else. Okay? Now, this is called the systematic approach. Why? Because you turned on your CCTV in the morning, and from throughout the day, whatever the routine I am following, you are systematically following that. Okay, basically systematic. Another is random. Okay, random is that it's basically I have selfie. I say so someone like spy I have put in your room, and he randomly clicks photos whenever you are drinking. Okay, so it's random. You don't need to sequentially do that. And then randomly he takes photo, and then he basically takes all the photos at the end and see in how many times in that photo you are drinking tea or coffee. And based on that, you also can make the analysis. The beauty of this I'm not going to comment on what is the good or bad part. Okay, let's just leave it that part because that's debatable. But these are the two approaches. So one is that you are continuously moving from one place to another. Okay, and then you are basically saying that, okay, morning I have taken coffee, evening tea or something, and you are basically making the judgment whether what I like. Another is that I'm randomly in the evening, today's evening I took the photo, tomorrow's morning I took the photo, and again day after tomorrow I took the photo. Randomly I am taking photo anytime, and then I am taking all the photos, and then I'm analyzing, okay, what I like. This is called the stochastic or random search method. Okay, and both have its own merits and demerits. Okay, rather than I'm commenting on that this is good or bad, I would say that what kind of software are actually going to use this kind of method, that is more relevant. But anyway, even this systematic method, they are having two different flavors: exhaustive search and fragment based search. Okay, and these are Monte Carlo genetic algorithm taboo search. I'll talk about that very quickly. So exhaustive search is what? It's basically one classification of systematic search algorithm. Now what I am talking about here, that I have to, what is the objective here? I am playing with the conformation, because I quickly want to find the pose which will fit into the pocket, isn't it? So that means I have to quickly find it. Means basically I have to play with the rotational space, torsional space, translational space, and torsional space. And here it particularly focuses on the torsional space, where basically with this number of conformations. So if this is the number of conformations capital N, what it comprises of? First one is this I. It is basically I equal to 1 to N. It's basically depending on the size of the molecule, it finds that how many number of rotatable bonds you have. And then this is called the J. J is basically increment, means basically systematic. So for example, the recorder, the CCTV you took it, right? So if I do like this, it will not be able to capture, because the frame rate, my movement speed is so high, it will not be able to capture. But if I do like this, probably it has a frame rate which can capture this movement. So right, this is called the spacing, okay, the theta ij, this incremental angle change, okay, and that also you want to do multiple times, and this is exactly you will get number of possible conformation, and this is very, very systematically you are doing it. And then the moment you are having all the possibilities ready, so you basically try to mix it with the rotational and torsional, rotational and translational space, okay, and then you will be able to generate lot of conformations. Another is even interesting, okay, this is also I personally like a lot. This is called the fragment based search. It's very simple. You have a molecule, you break down into small fragments, okay, and then what you do is that take the bigger fragment, okay, this one, and then you first dock it over here in the pocket, and then slowly you try to grow that molecule using the additional smaller fragments, right? And then finally you will get the final molecule dock. This is also very systematic approach to this fragment based docking, okay. So these are the systematic based search algorithm. Our focus is what? To find out the conformation, okay. We are not talking about scoring as of now. Then another is the stochastic. This is what we call the randomly we are taking photos, okay. So basically if this is the energy landscape, you are basically randomly taking photos at every point over here, and then you are assessing the energy, and whatever is best, that is basically your solution. Now in this one there is something called the Monte Carlo based approach. Now think about this energy landscape. Here protein ligand, they are making complexes. Now each and every complex, they will be having different energy scale. Now if I probably I am hyper right now, but a few minutes back I was a little bit in the lower energy state, so I was very much stable there. So whatever the energy well you are saying that lower energy well you will be having, that is very stable state. So what Monte Carlo approaches does is that basically start with a conformation, and it calculates its energy, and then it generates poses through bond rotation, all the three variables randomly, and then again it calculates the energy of the second complex. For example, this is say EA and this is say EB, okay. Now the question is that I am already stable here, why I should see solution is here, this is the binding pose, this is where I want to go, I am here. But my first question is that if I have to go here, then anyway I have to come over here, right? Otherwise I can't go. Now the point is that but why should I go there? Because this energy is not favorable compared to this. Why should I go there? That is the beauty of Monte Carlo approach. That this states that usually it should not go, but there is limited probability, maybe 5%, 10% chance that it can go from this well to that well. Okay, and you know that if it goes to this well, then only you can come to the solution, right? So that is the beauty of this Monte Carlo based algorithm. It's called the Metropolis algorithm. Okay, but I'm not going to talk about it. But this conception that lower energy, yes, it is desired, okay, but it doesn't necessarily mean that little bit unfavorable energy states are not possible. It is not true. Okay, that is also true, but probability will be very less. Clear? Okay, now this is the genetic algorithm. Okay, this is probably if you have used I don't know, there is an open source software called Autodoc. Okay, but this particular algorithm is tremendously being used, and this is nothing but the random search algorithm, one of the kind of random search algorithm. What you do is that, so any molecule you will be having, you basically define it in the form of a vector, and this vector will be containing what kind of information? Your coordinates of that particular molecule, maybe the center of mass coordinates, then what is the degree of, your axis of rotation, and all the rotatable bonds and their possible configurations. and these basically becomes your chromosomes, multiple chromosomes like that you have randomly. You have already defined all of your probable conformational states. Basically, you have multiple chromosomes. Then simple genetic algorithm does is that is probably you know better than me. You basically do a lot of studies like genetic operations like crossover. It's like some part of the gene you take it out and some part of the gene you take it out from other chromosome, and then basically you create a new baby or children. Sometimes if it is required you do some mutations as well, and you are doing it this entire activity normally. Okay, so first is what you have to define a molecule in the form of a vector, and then you are doing a lot of manipulations here. And what finally you are going to do, you are every time or every step you are basically going to calculate the stability of that particular complex. Okay, and that will basically dictated by scoring function. I'll talk about that in later stage, but there is some filtering to do that. But this is the way you are basically going to generate lot of confirmation. And there is another thing called taboo search. Taboo search is basically telling that, okay, say, for example, one ligand conformation I'm exploring and I found that it's not working. Okay. So if it's not working, then make sure that whenever next time I'm doing the search, okay, it should not repeat the first. Again, I'm telling you, this is the random. Random means it can happen that randomly I took today morning 11 o'clock photo, tomorrow also randomly I took the same photo. It is a mere coincidence, but it can happen, right? So to make sure that doesn't happen, that at least I should, when I take the photo, it should not be the 11 o'clock in the morning. Okay, so that time I have to remember that, okay, last time I took the photo in 11 a.m. So the moment it's remember, you know, right? When we all of us written exams, remembering things is very difficult. After exam only that will go away, right? So it basically means it's very memory intensive work. Computer will crash, man. Understand? Understand? It's whenever you are trying to remember, putting a lot of stress to computer, it will say no. So this is not very preferred approach. Okay, these are the list of softwares. Okay, particularly I would talk about Autodoc because this is the open source. Probably you can try it out, and it has a stochastic, as I said, random search algorithm, and which is quite popular. Okay, you can use that one, but there are many other softwares which you can try it out. Okay, but one quick trick for conformational search is probably grid box. Probably when you will be doing the hands-on, you'll come to know about it. So conformational search space is huge. Okay, so that's why if you are little bit become logical or some experimental data you have, that will ease your life. So whenever you are talking about, sometimes you'll hear this terminology called blind docking. Blind docking means like I do not have any idea this ligand is going to bind to where. Okay, but at least if you have some idea, then probably you can define the active site. Around it you can limit your restrictions of the movement. Okay, that will significantly ease your calculation. And again, I'm telling you, there are a lot of repercussions. More and more complex you make your calculations, you are not in the millions now, you are basically in thousands, hundreds. Yet you are coming down. Okay, so be smart, be optimal, and basically based on that, you basically, if you define a grid box, it will basically allow you to screen lot more molecules in a given time. Okay? So essentially these are the benefits: they reduce the sparse search space and provide quick convergence. Okay, so now since I talked about it, then I'll just quickly go over this scoring function. But this is also equally important. As I said before, okay, scoring function is the one which actually assess that the pose which you have generated, whether that is the desirable one or not. Because at the very beginning of my definition of the docking, I said that when two molecules fit together to facilitate favorable interaction, this favorability is basically defined by the energy landscape, basically by the scoring function. So for example, if you have the I don't know whether you are able to see it or not, you have this, for example, this is your protein and the ligand. It is happening when they are independently, they are sitting, they are attaining a different energy states. But when the complexation is happening, it is, they are becoming stable. So that's why, so this complexes energy will be lesser than the individual components of it. That is what exactly you are seeing in the binding affinity expression. Okay, this delta G binding in energy is nothing but the difference between these two energy levels. So just think about it, this is the E complex minus E1 plus E2. Now, how these energies are being governed is basically interaction energy and as well as the solvation energy and entropies. Okay? Now, these classes of scoring function which we talk about is that complementary scoring, force field based scoring, and empirical scoring. Now, complementary scoring is nothing but you are basically dividing your molecule into several segments. So, hydrophobic, aromatic, polar, hydrogen monomer, acceptor, and stuff like that. And basically, the same thing you are doing for the ligand, and then basically you are checking the compatibility. So, basically, it's like that. So, I cut my hand, and this I cut my another hand, then I can do the handshake. I cannot do like this. So, it's like that. Though I told the shape-based complementary, which but think about the same analogy in the interaction landscaping as well. There is one popular web server, Patchdoc, which you can try with. It's especially very helpful for the bigger molecules. Okay, when you have a very big molecules are there, maybe like biomolecules, Patchdoc, and there is something other called Haddock and all that. You can try it out. But many of those cases, like they use the shape complementary approach. Another is the force field based. So whenever we talk about interaction between two molecules, it is mainly driven by electrostatic interactions and the van der Waals instruction. Electrostatic interactions is nothing but when the molecules are carrying charges, right? Based on that, you can have this energy function. And the van der Waals interaction is basically the short range interaction, which is basically predominantly repulsive but attractive as well. So whenever there are two particles, they are far apart from each other, there will be some attraction going on. But when they come closer to each other, then repulsion is going to happen. Why? Because when they come closer to each other, in the outer shell, the electrons are there, so they start to repel each other. Okay, that's why. Otherwise, they are going to be attractive in nature. Okay? But apart from this, also this is called the extended force field. So apart from the electrostatic and van der Waals interaction, you can also have hydrogen bond or solvation contribution, and they are also in the form of these equations. Okay, I'm not going to go into the nitty-gritty details of the equations, because that itself is a topic at its own. But one thing I would like to highlight here, that here you will see some the W VDU, WH bond, W elect. Okay, these are basically the weight factors. It's just not the. This is the only difference between the force field and the extended force field. In the force field, this weight you have only VDU and the electrostatic and van der Waals, and these weights have coefficient 1. These values are 1. So, but it is straight away van der Waals plus electrostatic interaction, you are summing up. But here, since you are adding additional terms, so you have to additionally scale it up and down. These are basically done to some numerical fittings against the experimental data. These weights are being obtained. Okay? Now coming to the empirical part. Okay, this empirical part is basically it has the same energy components. But earlier, what I said into the force field based scoring, you have a formula. See, there is some whatever it is the formula, you have at least the formula. Basically, you really do not need to know anything about it. If you have the formula, you plug the values and you will get your solution. But the problem with this empirical scoring function is that you do not have formulas also for this. Okay, and essentially these are basically what happens. You do have experimental data, and you are going to your experimental data means like your binding affinity data, and you have the complex, and there basically now you are going to back calculate all those terminologies, and time to time the form of these functions are going to change, the weights of the functions are also going to change. Okay, it's empirical. Okay, so basically it's evolving. So today say I am developing a scoring function based on 100 data points, and after 10 years 1 lakh data points, everything will change. Your definition of van der Waals or Coulombic may also change. I don't know. Okay, that may happen. But now this is one example. This is basically one popular software is there, commercial software. Okay, it's called Schrodinger suite. So they use this particular score. They also have different versions, but in general, I say the glide score. But they have this kind of scoring functions are available, and really you don't know this functional form of these things. Okay? But only one thing I can tell you that they have decoupled into many additional terms. Okay, the lipophilic interaction and all other kind of interactions, they are also decoupling it. But purely empirical is nothing but okay that you have experimental data and you are doing it. It's not like that. If you don't if you know or no, I don't know that for example Newton's law of motion or any undercurrent model, they are basically you know the mass, you know the acceleration, you know the what kind of force is being applied. Okay, Here, what is happening? You know the force, okay, and you don't know anything else. Now you are basically trying to back calculate whatever fits you where, and then you can define whether it is mass or acceleration, whatever you want to define. That's up to you, and the definition of itself is going to change later on. Okay, and there are again this one I have said that Autodoc. I'll just particularly why I'm highlighting. I'm not advocating any particular software or any platform. Okay, I wanted to make sure of that. Only thing I wanted to talk about Autodoc is because it's an open source software. Okay, it is very easily available to all academic people. But other things also you can do, and they are available in different frameworks. Only thing I said that Autodoc and Autodoc, force field based and empirical for a reason behind it. It's basically that one case like it is using the force field based, another case extended force field based. That's why they put it into the different category. I think Vina is also Vina. I think is empirical. I guess I'm not sure. Empirical plus knowledge based. I guess. Okay, now this is the part. I'll be very fast. Okay, but that AIML driven molecular token. This is the why I want to be fast and I want to be brief because I want working in this area, so I don't want to reveal what I'm working on. Okay, so that's why I'll be very fast. As simple as that. So majority of the AIML work currently is going in this docking space. They are playing with the scoring function, particularly empirical scoring function. What I said for empirical scoring function development, you don't need to know any physics, chemistry. You have experimental binding affinity data, and from there you are going to define that what would be the binding. It's basically back calculation you are doing. Okay? And for that, there are very popular platforms are available, not scoring functions are available. Gina, Spina, and Glide. Glide is basically I talked about it in the empirical scoring function itself, but this Glide afterwards, after some time, they are basically very much into the deep learning methods. So whatever the empirical scoring function which I have showed, these are mostly linear regression kind of models they've used. Those are the older versions, but now they are into the deep learning kind of models. So that's why these two models are very popularly used, and also the Glide. And mostly they are not playing on the searching space. Okay, they are only tuning the scoring function, so that the whatever pose you get, at least you can tell that whether that is required for you or not. Okay? And there is another group of algorithms. Again, this is what is that called? Deep learning algorithms are being used, and these are basically combining both search selection as well as scoring function, modifying scoring function. I'm not going to the technical details of it, just to remember those names, okay? So that you can get a perspective where the AIML is going. By the way, that deep learning is, AI is the bigger version. One branch lower is the ML, and one branch lower is the DL. Basically, DL is the subset of ML. Okay, deep learning. Now there are things called equibind, tank bind, diff talk. Okay, these are the combination of search pose as well as searching the pose as well as modifying the scoring function. They actually work in both the spaces. Okay, and out of that, I will talk about deep dog in particular, why I'm very excited about it. So this is done developed by MIT people. Do you know who has developed it? Electrical engineers. This is the beauty of this kind of research, is that at some point of time it is so much physics and chemistry and involved, and mathematics is involved. One particular department or particular branch cannot handle it. This has been done by the people who have no idea, who have not taken any course on protein, any course on ligand, substrate, drug, anything. They have developed this thing, deep talk. Okay, I'm very curious about it, and like if anybody wants to do collaboration in this aspect, I'm very happy to do that. But anyway, what the point is that this is basically with the principle of reverse diffusion. I'll explain it. So, for example, first let me explain the diffusion first. So, you have a bucket of water or a glass of water. You have you put a drop of ink and you just wait. Slowly, you will see that the ink drop is basically getting diffused across the water, and finally you are getting a homogeneous solution. Now you rewind it. So now you have a homogeneous solution, and you are basically rewinding your movie, and you are seeing that okay, from starting from homogeneous solution, slowly, it coming to the drop of that ink. That's the rewinding. It's called the reverse diffusion. So what the principle over there using is that you have this receptor and the ligand. They're randomly thrown the same molecules in different conformations, orientations, and whatever to the molecule. You see this everywhere, right? Now, basically, it is the final state of diffusion, right? Now they are rewinding it and rewinding it, and you see here that majority of the molecules are clustered into one pocket, and some of the molecules maybe it's in the different pocket. So then they have defined, this is another way of doing blind docking also. They have defined that this is probably is the right pocket for that particular target. Now they have a unique scoring function also. It is nothing to do with the binding energy, but it's similar to binding energy. And in that, like this particular ligand is also in different poses, upward, downward, and based on that, their scoring function, they are ranking these poses. Okay, this is basically very state of the art method which is being used, and it is being basically used by in different aspects, like even like the protein modeling also, this kind of methods are being used, this approach is being used, reverse diffusion. Okay, and they have claimed that they have outperformed many of the existing what is that called, AIML algorithms in the predictions. So predictions means, what do I mean? Basically, when you have a when you are redocking something, so within 2 angstrom, if the ligand conformation lies, then basically it means that your prediction is pretty good, and that's what they are doing. Okay, out of 100%, 20 to 25% of the time, they are basically identifying the right pose. So beyond molecular docking, one slide I have, I will just tell you. Okay, we understood molecular docking. Wow, what a great thing we have learned. So there is no limitation. Can you please tell at least one? I mean, I know that I've seen it. So when there was COVID, right? I was working in Saravati. I used to work. I was working on the drug repurposing. So I had existing libraries of molecules. I mean, drug molecules, and I found some protease, and I was doing docking and enjoying and all. Then what happened? You know, none of these are working. So after all this talk, 45 minutes or 50 minutes, I don't know how long I have spoken. And after everything, nothing is working. Understand? And that will happen. That will happen. Not that did not. It's not, and it's happened, and it is accepted that it is going to happen. Okay. Before going to that, what is it? Oh wow, this red color bar is popping up. Okay, it's over. It's defeating everybody. Good for publication. 100 times you do that, 25 times you are going to get the right pose. I'm just giving an example here for the AIML doc, but this is the reality. 25% of the time you are going to get the right pose. 75% of the time you are not going to the right pose. So that means if you don't know in which bracket you are in, you got a pose and you thought that okay, this is what it is. Then you want to do the molecular engineering, and everything what you are going to get, your hypothesis, everything is now at risk. Be aware of it. So whenever you are using it, be aware of it, the limitations of it as well. I started, I'm sorry that I had to go back, but it is important. But if you recall, anyway, I'll not go. If you recall, I was talking about the semi-flexible docking and flexible docking. And that time I showed in one corner that small protein, it was dancing. And I said that it will be really, really computationally intense if you take into consideration of the entire protein flexibility. So we purposefully select a very small section of the protein to be flexible. In particular, to say the active site, and not only the entire active site, maybe 2-3 key residues which we assume are interacting with that particular ligand. Okay, because that assumption itself is causing us a loss, and this is what it is outcome. The 75% of the time which you are seeing, that active site rearrangement can also happen due to the bulk motion. Far away from your protein, maybe 30-40 angstrom far away, some loops have gone from this side to that side, and all the active site rearrangement has happened. So the moment you start keeping your protein fixed, rigid, or maybe you are partially make it flexible and you are keep trying to do the docking, it is may not be the right solution. That is the reason that we also have to think that molecular docking is good because molecular docking has one purpose, because here we are talking about millions of compounds, billions of compounds. Okay, but we have to also understand the gap, like what it is not addressing, and that's why we are going to talk about the molecular dynamic simulation. Anyway, this is the traditional part. I'll show you one case. This is very funny. So this is the protein is dancing, right? So, but I did not consider the dancing part of it. Maybe some part of it I have considered. What happened? I docked a molecule, then I ran some simulation. It is coming out. It was very giving very good pose, nice interactions, good docking score. I was happy. Everybody was happy. My manager was happy. About to get the promotion. Then I ran this, and then my promotion got stopped. So that's why I'm saying that. But this kind of approach, this molecular dynamic simulation, you should not do when you are in the discovery mode. Okay, if you really are in the fundamental study, why for this particular molecule, when you have a narrow set of molecules, that time you do this kind of computation, because this is very computational demanding, I would say. And this time, this your computer may cost you around 20 lakhs. Okay, not like 80,000 anymore. So please be aware of it, that you want to do this kind of calculations when you are really sure. Okay, maybe like 20-30 molecules, 50 molecules you have, that time you do. I'm saying in our capacity, big companies still they can do that, but still they cannot do in millions. Like still they can be doing 5,000, 10,000 simulations such like this can do. And but beyond that also you can do a lot of free energy calculation. Okay, by the way, I want to see compare this energy potential, because I talked about free energy. So okay, my ligand, I docked it. My ligand was, this is the active site. Okay, my ligand was very happy during my docking, but when I ran simulation, it is coming out. Now, what this energy profile, what it is telling you, that you know that in the energy profile, wherever you find the well, that is the best possible case. And what you see that when the ligand is in water, that time you have that the depth of the well is increasing and increasing. Means it loves to stay in the water, man. You forcefully use the software and ensure that it is going to the pocket, and then you are happy. Okay? It should. I mean, those are the things like you have to understand that why it is not capturing. There are many other issues also. Scoring function, there is an issue. Conformational space searching, there is an issue. But still you have to understand, you have to appreciate the importance of docking. The message what I wanted to give is that molecular docking is worthless. No, purpose of having every tool is different. It is for screening. Okay, when you have a thousand millions of compound, it is going to give you some molecules which you can further do your investigation. It is not the absolute thing that after doing molecular docking, then you are straight away going for synthesis. Your company will be bankrupt for sure. With that, I would like to summarize. Okay, so this is basically, I talked about overview of molecular docking, its application, and essentially I told you that in which application area we can use molecular docking, and I also have demonstrated several case studies to strengthen my point. Then I talked about types of docking. So here I talked about the principles of docking, and then how those principles have to be implemented into the docking software. And if we do that, then how traditionally these are being called, like rigid docking, semi-flexible, flexible, and all. Then we talked about also search algorithm. So basically, what are the algorithms we should use to find the best pose? Okay. And then we also talked about scoring functions. This I did not talk much about it, but it's basically the typical interactions we can imagine of. And finally, I also talked about some not much, but little bit of update I wanted to give you in this AI/ML aspect, right? And finally, I wanted to make sure that when you have a reasonable number of molecules, you should definitely do the following steps. Okay, I think that's why there are several hands-on sessions and lecture series are there addressing this particular area as well. So I'll request you guys to look into this part. With that, I would like to thank you all for your time, and I'll be more than happy to take your questions. If not, I'll. No. Those kind, nothing. It is just interaction. Yes, biocompatibility study, you want bioavailability study, toxicity study, nothing. It is purely comes from a different perspective. It, as I said before, please remember, it is not about protein or ligand, receptor or anything. It is two molecules, it is going to interact. And whether it is going to happen or not. Happen, when I'm saying, is that it is going to happen favorably. That is this application. I'm objective. How you are going to exploit it, that is for sure, but not definitely, at least in my knowledge, it is not. No? Okay, thank you. Off na?
Thank you so much, sir, for enlightening us on the current future trends in the molecular testing in depth. I now request our coordinator of the workshop, Dr. Arya Ambika ma'am, to present the memento and certificate to our speaker as a token of our gratitude and appreciation. Now we'll have the lunch break. At sharp 3, we'll start with our next session.